Good evening. My name is Alessandro. I'm going to talk to you guys about flooding and its correlation with mosquito-borne disease spread. So the name of my paper is Extreme Flooding, a Driving Factor of Mosquito-Borne Disease. So before I start talking about all the data that I found and share it with you guys, I want to give a brief introduction into what we're going to be talking about today. So as we know, flooding is extremely impactful on human health and national security. It costs millions of lives and billions of dollars. And of course, we know mosquitoes carry diseases like dengue, malaria, Murray Valley encephalitis, Rift Valley fever, West Nile virus, and many more. And we know that flooding and mosquito spread or mosquito prevalence is correlated. Why? Well, mosquitoes thrive in environments with stagnant water, which commonly arise after heavy flooding. So what stagnant water is, of course, it's pools of water that don't move. They're stable. And what they do is they allow these mosquitoes to lay their eggs and breeding to occur. So why are we concerned with mosquito-borne illness? Why are we concerned with controlling mosquito-borne illnesses? Well, they're actually very good at spreading, especially during flooding. And we're worried about certain areas that have poor vector control and poor flooding response. So we're actually going to talk about the mechanisms that cause the proliferation of these mosquito-borne illnesses due to flooding, and how time periods and locations with flooding have high incidences of mosquito-borne disease, and why lagged effects, which we'll talk about later, of flooding are an important part of understanding and preventing the spread of mosquito-borne diseases. And we're going to talk about whether these factors are statistically significant, whether we have to worry about them, or whether we have to do more research to truly understand them. So here we have a box plot. And it's comparing rural areas and urban areas in a certain place in Africa. This is by Nosra et al. 2021. I really recommend this paper. So this box plot graph is showing that rural areas actually have higher abundance of mosquito eggs. They found a higher abundance of mosquito eggs of Aedes aegypti mosquitoes compared to urban areas. And this is because rural areas can actually absorb water after flooding, creating these stagnant, stable pools where these mosquitoes can lay their eggs and increase mosquito populations. Urban areas can't really do this because due to the concrete or other infrastructure, these pools the water cannot be fully absorbed and create small pools where these mosquitoes can lay their eggs. So this water is ever flowing and these flooding out effects happen. The water is always moving and possibly killing the mosquito larvae. This paper by Ding et al. Shows that there is a risk of malaria with each of these factors, and we're going to go through them together. So AHR is the average hazard ratio, which means the risk of something. So when you have an average hazard ratio of 1 or less than 1, it's a normal or less than normal risk of whatever we're studying. And here we're studying the risk of contracting malaria. So anything higher than 1 means that there's a much higher risk of contracting malaria compared to the average. And here we have 5 models and 3 treatments. So we have flooding alone, waterlogging alone, and both flooding and waterlogging. And we know that waterlogging is a variable or a constituent of flooding. So flooding causes waterlogging, which are these stagnant pools, as we discussed earlier, either in vegetation, in containers. In third world countries, it's very common to leave water containers out for collection, but this is not good after flooding because obviously this water is undrinkable, but it's also not thrown away. So you get these mosquitoes laying their eggs and proliferating in there. So what this paper is showing is with 95% confidence, the average hazard ratio with flooding alone of risk of malaria actually is increasing by a good amount, almost 50%. So from 1, you have here, it's 1.7. For model 2, you have 1.7. For model 3, 1.5. For model 4, 1.6. And for model 5, 1.5. I'm showing you an average of around 1.6, which is a huge increase in risk of malaria. And if you look at waterlogging, it's even higher. And we expect this, of course, because waterlogged areas are the environments that mosquitoes are looking for to lay their eggs. But when you look at them together is where the true concern lies. We see almost a triple increase in risk of malaria. That's the highest one. You can see it in model B, but an average of 2.5 hazard ratio is what we see here. And this is, of course, due to how flooding brings pools of water that are uh, habitable for these mosquitoes to lay their eggs, and waterlogging from infrastructure that's not well drained, such as attics that may pool with water, and maybe there's a hole in the roof, or streets that have potholes in them. So these things are actually very important when understanding flooding and its relation to mosquito-borne proliferation. I mean, mosquito-borne illness proliferation. So this paper here by Anyaba et al. Was actually a study on El Nino years, and what El Nino years are years in which the weather tends to be much wetter and cooler, and El Nino years are seen to be are becoming more prevalent throughout the years due to climate change and whatnot. So it's something definitely to be on the lookout for. And what the study was doing was actually looking at vegetation increases and mosquito increases with El Nino years. And the ones that we're concerned with here are in Australia and in South Africa here. So in South Africa, this area called the maize triangle or the corn triangle, it's known for its vast amount of vegetation. And what the study found was that during the El Nino years, 2010 through 2011, they found that a 43% increase in rainfall brought extreme flooding and actually increased vegetation a huge amount, which allowed, after flooding, these stagnant pools to form. And actually, they experienced huge epidemics, well, a bunch of epidemics throughout South Africa of Rift Valley fever, because these mosquitoes were laying their eggs in these pools around the vegetation during these El Nino years. And they had actually not seen something as impactful as these epidemics since 1970. There had been no epidemic as big or even as important of Rift Valley fever since 1970. And the same thing was done with Australia, and they found Murray Valley encephalitis was huge during these El Nino years due to the increase of vegetation and this pooling of water. So these areas that experience flooding are actually seen to have much higher numbers of mosquito-borne illness prevalence compared to other areas throughout the world. And in red, here is Rift Valley fever, and in blue, here is Murray Valley encephalitis. So pretty cool. So this paper looks at the effect of El Nino years and mosquito-borne illness prevalence in certain areas, specifically in South America and Central America. So this graph here is talking about, it's referring to a river in Peru called the Piura River, and they're looking at the amount of discharge or overflow of the river throughout the years. So you can see they're labeled 1958 all the way to 1998. And what you can see here is that the main overflow or overflooding of these rivers is seen during the El Nino years, and it has actually increased throughout the years. So you have in 1965, you have an El Nino year, you have 1972 El Nino years, and then you have major flooding or overflowing from 1984 to 1998. And we're going to couple this with malaria incidences in Peru soon after I talk about this. But so as we can see, there's really no overflowing of these rivers without El Nino years, apart from an anomaly here in 1989. These El Nino episodes are causing this river to flood or overflow, which is bringing stagnant pools of water thereafter, which is bringing malaria to humans. So we know mosquitoes are vectors of malaria, but what we're looking at here is we want to couple the graph on the right with the two graphs on the left. So what graph A is showing is malaria cases per 1,000 throughout the years. So you have from 1941 to 1998, and you can see after 1950, there seemed to be no cases of malaria. And this is because malaria was eradicated in Peru in this certain area that was studied. But a bounce back has been seen after 1989. So if we look at the graph on the right, we see that these El Nino years are bringing extreme flooding to this Pura River. And there's almost a positive trend, a positive slope that we can see there from 1958 through 1998. And this is similar to the slope that we see on graph A of figure 4. And what we can assume is that these El Nino years are causing overflow in these areas and bringing mosquitoes the perfect environment to proliferate and cause malaria to the population. Now, graph 4B is showing rate of change of malaria per years, and you don't see any data before 1972 because, as I said before, malaria was eradicated and there were no cases after, or very minimal cases of malaria in that area thereafter. Okay. So let's talk about lagged effects. So lag time is the time for something, or the wait period for something to happen after a certain event. And here we're talking about flooding and waterlogging, A and B respectively. And what we can see here is that the hazard ratio of malaria or contraction of malaria is extremely high for flooding, graph A, from day 22 to day 28. And similarly for waterlogging in graph B, it's from day 4 to day 10, or day 2 to day 12, if you want to be more broad. And as we can see that it's completely different times. So why is this? So we talked about flooding creating these stagnant pools of water. So it seems like maybe for the flooding to subside and stable pools to form, it takes around 20 to 28 days. And this is probably why we see a similar curve between A and B. We could put these on top of each other and actually put the peaks on top of each other. So we would see waterlogging happens from day 20 to day 28, possibly. There's no research that Ding et al. Conducted on this, but it is understandable that after flooding occurs, it takes a while for these stagnant pools to form. And it's important to understand these lag periods, because if we're going to control these vectors and intervene after flooding, we have to know the perfect time to intervene for the best effect, so that we can attack as many vectors as we can, and stop illness spread before it's too late. So this is an overview. This is a scoping review of everything vector-borne. So vector-borne illnesses, including malaria, dengue, cholera. And what this graph is showing, it's showing that there is a high agreement or high evidence that they see a lag time of 1 to 3 months in dengue when there's extreme rainfall or flooding. And there's a bunch of papers that they studied, and they found that this lag time is actually, that there's a huge range, 1 to 3 months. And for workers who try to control these vectors, these companies who work to control these vectors and understand how mosquitoes work during flooding, this data is invaluable. It's important to understand how or why the range is so long. So this could be for a multitude of reasons. It needs to be researched, but we can see that there's a high agreement between all these researchers, including Ding et al., which was one of my references. And this is not only, it's important to note that this is not only the case for dengue, but malaria as well, Rift Valley fever, Murray Valley encephalitis. These mosquitoes have the same or similar trends when it comes to the lag periods, because mosquitoes prefer stagnant water, and stagnant water occurs after a certain amount of time. And of course, different floods are going to allow stagnant water at different times. So it's important to really understand the variability in flooding, and hopefully one day we have better resources to understand this. Now, the last topic I wanted to go over is lag effects and runoff of nutrients. So now the last thing I wanted to go over with is runoff during flooding, increasing nutrients. So one thing that's not well studied, but Yi et al. Seemed to study a little bit, is how nutrients affects mosquito increases or mosquito growth. And I'm going to talk about possible growth of mosquitoes during flooding and how this can be coupled to the nutrients that is in the water due to runoff. So here we can see that there's an increase in nutrients in the water after flooding, which showed a massive increase in mosquito larva carbon and nitrogen composition. And they actually saw a growth in adults in the certain areas. So this growth was only prevalent in areas that had an increase in nutrients. They studied many samples at different locations, and they were looking at nutrient content in those samples, and they found that, of course, it varied because certain areas had animal droppings, leaves falling, and contributing to that nitrogen and carbon percentage. And they found that these mosquitoes that lived in areas with high nitrogen or carbon concentration in the water, they actually grew much larger, and the larva composition was much higher in relation to carbon and nitrogen. The nitrogen and carbon inside these larvae was much higher. And now the question is, how does this affect growth or speed of growth of these mosquitoes? Because during flooding, runoff can bring a bunch of nutrients to these pools of water that are created after the flooding subsides. So it's important for researchers to really dive deep into this, because there are certain ecosystems that are known to have huge nutrient abundance, and understanding how nutrients is coupled with flooding and mosquito prevalence would be a key factor in stopping mosquito illness prevalence. So I would like to thank you all for listening to my presentation. If you have any questions, please let me know. And thank you, Dr. Oberbauer, for the guidance during the development of this presentation.